Welcome back. We're going to continue on here with wave properties. Okay, the third thing that can happen when a wave hits something, okay, so we've gone through the first example, it hits something that it can't pass through. It's either absorbed or reflected. We looked at reflection. It hits and it bounces off at the same angle it went in at. And then we looked at refraction, and it hit a surface that it can go through, but it changes speed as it goes from one medium to another. Now, in this last example, it's kind of in between. It hits a surface that it can't pass through, but there's a hole in it, so it can go through the hole and bend around the hole. This bending around as it goes past a barrier is called diffraction. In diffraction, an object causes a wave to change or bend around it. Okay, the smaller, the narrower the obstacle, the more it bends. The less narrow the obstacle, the wave bends less. Okay, and sound bends around a door, so you can hear somebody. This is a good example of somebody talking in the hallway. So if you're talking in this room, the sound goes out the door like this. It bends. Okay, it begins to bend around. Like coming through a window bends and goes everywhere in the room. Think about it. When you have the window open, okay, it doesn't come through like a laser beam, just, a beam of light. It comes through the window and then it bends and it spreads out or diffracts all through the room. There's a little clip here on wave diffraction that we're going to take a look at.
Waves also bend as they pass the edges of objects in their path. For instance, an expanding ring of waves moves away from a stone dropped in a still pond. As the ring becomes larger, any short part of the wave front becomes nearly a straight line. But if the wave front passes through a small slit in a barrier, the wave coming out the other side will not form a straight line. Instead, it will spread out from the slit in a curved line. The transforming of a straight wave front into a curved front is called diffraction. The combination of diffraction and reflection explains why we hear noises around large buildings in hectic downtown areas.
This last example is, in the first three examples, we had waves hitting something. It hit something that it couldn't pass through, and it reflected. Then in the second example, it hit something that could pass through, but it changed mediums and it bent. And in the third example, it hit a solid barrier. There was a hole in it, so it could diffract, and part of the wave went through the hole and bent around the hole. Now, in this last example is when two waves bump into each other. And this is called wave interference. And it says it's the ability of two or more waves to combine to form a new wave. Okay? The waves pass through each other and continue on in their original direction. The new wave is created only when the waves continue to interact, which should just make common sense. The waves stop happening, then the interference is going to stop happening. That's all that's saying. If the original waves stop, then the combined interference is going to stop also. Okay? And there's two basic waves that can interact with each other. They can construct and add together to make bigger waves, or they can destruct and they subtract or cancel from each other, and the waves get smaller. So let's take a look at these two examples, and this is a pretty good picture. The first one is constructive interference. And constructive interference happens when the crests line up and the troughs line up. So this little crest plus this little crest add together to make a big crest. And this little trough plus this little trough add together to make a big trough. And then the next thing happens with the next crest, and it makes the two little crests add together to make a big crest, and the two little troughs add together to make a big trough, and so on and so forth down the wave. These two little crests add together to make the third big crest, and then finally the last little trough adds together to make a bigger trough. So this happens in the ocean. Sometimes these are called rogue waves. The waves will line up and they make bigger waves. So every once in a while, I go read something or hear something in the news. They call them rogue waves, these big waves. Okay. On the other case, instead of the crests and the troughs lining up, they're with each other. So crest to crest, trough to trough. they're lining up so that they're exactly the opposite. The crests fill in the troughs. Okay, so what's happening is this crest is lined up with this trough. So the crest is going to fill in, it's like, the mountain fills in the valley. And then the next valley is filled in by the mountain. And then the next mountain fills in the valley. And then the next one, the mountain fills in the valley, the mountain fills in the valley, or the crest fills in the trough. So if all the high spots fill in all the low spots, you end up canceling it out and the wave gets destroyed.
Another phenomenon occurring in waves is
You can see how some of these waves are canceling out here in the center, and some of them are adding together to make bigger waves.
interference. If the crest of two waves of the same frequency pass a given point at the same time, the waves are said to be in phase. Where the crest of one wave of the same frequency reaches the same point as the trough of another wave, the waves are said to be out of phase.
Okay, so this is a good example of what we had in the notes, except they're able to overlap them. So you can see here that all the crests are lined up with the troughs. So the crests are going to fill in the troughs and the wave is going to cancel out.
Waves in phase actually strengthen one another.
So all the crests are lined up. So all these crests are going to add up and all these troughs are going to add up to make a bigger wave. And this would be constructed.
Another, while out of phase waves cancel out each other's energy. The waves of light coming out of a laser are in phase and are therefore more powerful than the out of phase waves of light produced by incandescent lamps. The standing waves of stringed instruments are a result of interference patterns. As the string is attached at both ends, the waves created from playing the string continue to move back and forth along the string. At certain frequencies, the string will show interference patterns in which waves seem to vibrate up and down, but do not appear to travel back and forth along the string, thus producing standing waves.
And then the last property of waves is called resonance. And this is the tendency of an object to vibrate at its own natural frequency. And that means it's going to increase in amplitude at certain frequency. So it vibrates at this natural frequency and the object gains energy. So an example of this is an opera singer breaking a glass. They hit the natural frequency of the glass. The glass vibrates at its own natural frequency and it gains energy. Okay, now as the glass gains energy, it starts to ring and make a sound. Like glasses being glasses and being brittle don't vibrate very well. So if they vibrate enough, the glass shatters. Okay, so tuning forks, opera singer breaking a glass, musical instruments, bells, buildings are all examples of resonance. Now, in Tacoma, Washington, they built this bridge, and we're going to see how the engineers didn't really think about the wind speed in the area, and the wind speed passing over the bridge had its own natural frequency. Okay, because the wind had a speed, and when the wind speed matched the bridge's resonance or the bridge's natural frequency, the bridge began to vibrate. And we're going to take a look and see what happens.
Any object, when disturbed, tends to absorb energy by vibrating at frequencies that produce standing waves.
Okay, a standing wave is also an example of resonance. When you hit this glass, it vibrated at its own natural frequency and made that particular pitch.
These frequencies are referred to as the natural frequencies of the object. An object's natural frequencies depend on the object's weight, mass, and other variables. Even huge buildings have natural frequencies. The waves created when a building or other structure vibrates at its natural frequency can cause tremendous destruction.
Okay, so this is some actual footage of this bridge that they built in Washington, Tacoma, and it's a good example of resonance, so let's take a look.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are...
Now, notice how the bridge looks like a standing wave. So there's some resonance at which this natural frequency or resonance at which this bridge wants to begin to vibrate, where the wave length is matched. So what was the problem with the engineering is that they didn't really think about the wind speed in the area when they designed the bridge. They should have changed this wavelength. So when the wind speed matched the bridge's natural resonance, it began to vibrate, which resonance is the ability to vibrate at its own natural frequency and gain energy.
Some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. Only at 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing.
So that 35-mile-an-hour wind is matching the bridge's own natural frequency or resonance. So the wind moving at 35 miles an hour matched the bridge's frequency or resonance, and it's causing it to vibrate. Of course, it's made out of steel and concrete, so it doesn't vibrate very well.
Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
We're going to stop here, and I want you guys to answer these questions on your own, and then we'll pick up here next time. I hope you're having a great day, and we'll see you next time.